No, 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 no. It's just, never mind. All is good. It seems it's working. And we're live on YouTube. Great.
The YouTube is on and you'll start the recording just before introducing the speaker.
I will do this. Yeah, let's wait another minute. All right, you ready to go, Zohar?
Yeah.
Okay, well, welcome back, everyone, and welcome to this week's seminar. We have with us Zohar Komargodski from the Simon Center, and he'll talk about higher central charges and gapped boundaries. Before the talk starts, let me say that during this talk, possibly others in the future if it goes well, we're allowing participants to unmute themselves and ask questions whenever you'd like. Zohar is happy to answer questions on the spot. Otherwise, if you'd like, please write them in the chat, and either Zohar or one of the hosts will pick them up. Right, so Zohar, thanks very much for joining us, and take it away.
Thank you so much, Yuder. Yeah, thanks everybody for coming. At any point, if anybody has questions, comments, corrections, please interrupt. So one title is higher central charges and gapped boundaries, but you can also think about the subject as beyond gravitational anomaly for reasons that I'll try to explain. This presentation, this talk is based on work that's hopefully going to appear soon with Justin Kaidi, Kantaro Mori, who is now in Tokyo University, Sahan Saif Nashri, who is my student. He's also applying this year. He's exceptionally good. And Shuheng Shao, who is currently in Princeton. So this talk is going to be more or less exclusively in 2+1 dimensions. I'll make some remarks at the end. Well, 2+1 dimensions and 2 dimensions will appear on various occasions. But the talk is about properties of systems in 2+1 dimensions, perhaps with a boundary that is 2-dimensional. So let me start with some very brief introduction that I'm sure is not necessary for this audience of experts. So it's been very well known for several decades that if you have a non-trivial topological phase in 2+1 dimensions, you could think about the Chern-Simons theory to be concrete. You could think about an abelian Chern-Simons theory like U1 gauge theory at level K. It's been well known, experimentally verified. There are Nobel Prizes for this, that there are chiral edge modes. The edge is this blue layer. So if you try to take a quantum Hall, integer quantum Hall state, put a boundary, there are chiral bosons moving on the boundary. This is by now a very well-known observation that we understand theoretically. We have seen it experimentally, and so on. Similar phenomena exist for non-abelian phases of the quantum Hall system, and so on. So this is the big. So U1 level K Chern-Simons theory, just to be succinct, and it's just this Lagrangian where A is a U1 gauge field. Sorry, so A is a U1 gauge field. Is a U1 gauge field. in this notation of mine. There is a very important distinction mathematically between the case of odd integral k and even integral k. If k is non-integral, it should not be regarded as a 2 plus 1 dimensional system. It's secretly a 3 plus 1 dimensional system, and I'm not going to discuss those cases in this talk. In this talk, my 2 plus 1 dimensional systems will always be well defined in 2 plus 1 dimensions. So this talk is only going to be about the non-spin case. What is, you can think about it as bosonic theories. We presume that a lot of what I'm going to tell you can be extended to the spin case. But just to be on very safe grounds and to be very explicit, I'm going to discuss only bosonic states in this talk. The bosonic states of the quantum Hall system, or bosonic topological field theories. Okay, so when you try to understand this problem of what happens at the boundary of a topological phase in 2 plus 1 dimensions, you have to pick boundary conditions. It's always like that in QFT, we have to pick boundary conditions. And there are actually tons and tons of different boundary conditions. The well-known fact that in the quantum Hall state, you get a chiral boson, a single chiral boson on the boundary, is due to a very specific boundary conditions that are picked in that system. There are different boundary conditions that you could have picked. So it's up to you. So there are various possible boundary conditions, but you can prove a theorem, which is going to be a trivial special case of what I'm going to explain, that doesn't matter which boundary condition you would pick for U1 level K Chern-Simons theory, there would always be something gapless on the boundary. Okay, so all the possible boundary conditions lead to gapless modes. You could have chosen more complicated boundary conditions, which lead to not a single chiral boson, but something much more complicated. But it would still admit that there would always be gapless boundary states. Doesn't matter what you do and which couplings you add or which boundary conditions you choose. Okay, this is a statement that that I have not proven yet, but I'll soon give you a proof. So as I said in this talk, we are only going to discuss non-spin theories, namely bosonic theories. And the setup is going to be that the 2 plus 1 dimensional system is a topological field theory. So it's you should think about it as some state of the quantum Hall system, or a topological field theory that you can realize on the lattice or in quantum field theory via some RG flow. And topological field theory is a set of anyons, A. Sorry, I'm using A both for the gauge field and for some anyons. I hope this would not cause a confusion. Anyons can move in space-time. And one of the most important pieces of data that specifies the topological field theory under discussion is how anyons fuse. So you take an anyon A, you bring it close to an anyon B, and you can decompose it in terms of some, single anyons C with some coefficients, which are this NABC. So that decomposition always exists, and it's part of the data of the theory. So the one very interesting question that you can ask, this is very interesting both physically and mathematically, is whether there is some choice of boundary conditions which are gapped. So the black box, sorry, so the data that you're given, or the data that you're provided, is a certain 2 plus 1 dimensional topological field theory, and you want to run all the possible boundary conditions, which is in principle an infinite set. But suppose you want to ask, is there some choice of boundary conditions which are gapped? This might seem impossible at first sight because maybe some of you have the intuition that if there is a topological field theory, there are always chiral edge modes. But in fact, for some special topological field theories, there are gapped boundary conditions. Now, let me say a few words about what kind of boundary conditions we allow. So in principle, I allow any boundary conditions that you can imagine, as long as the topological field theory in 2 plus 1 dimensions is not affected. So I fix the 2 plus 1 dimensional bulk physics, but the boundary conditions are up to you. So more concretely, you can add whatever you want on the boundary, and you can couple this stuff on the boundary in however way you want to the bulk fields, but it has to be local. So you can add whatever you want. So you can add here whatever you want. And you can also couple this whatever stuff you've decided to add to, let's say, the gauge field A at the boundary. Okay, so you're pretty much free to do whatever you want.
Zohar,
Yes.
do you assume Poincare invariance on the boundary?
I'm thinking, give me a second. I'm thinking of whether this is actually important for anything. Yes. Yes.
Okay, thanks.
There's a point in some of the theorems that I'll prove where this is assumed. So I'll assume that that we have Poincare on the boundary. Not for all the theorems, but some of the things I'll quote depend on that assumption. So you can add whatever you want on the boundary, but you are not allowed to change the bulk. More precisely, you're allowed to change the bulk by invertible theories. Invertible theories are just classical theories. So we don't change the quantum physics in the bulk, but we may change some contact terms. For invertible just means change some contact terms. So there are some special 2D theories which are completely well defined in 2 dimensions, but they may have a 't Hooft anomaly. So the 2 + 1 dimensional bulk that's required is not a topological field theory, it's just a contact term. These theories have a standard Alvarez-Gomez with an anomaly, and the simplest example, and in fact it's the minimal example, it's not just the simplest, but it's the minimal example, are just chiral bosons moving on the E8 lattice. So this theory has a gravitational anomaly. It has C left minus C right equals 8. But it does not require a topological filter in the bulk. It only requires a contact term. So it has a standard 't Hooft anomaly. If, for example, the boundary has a single chiral boson, it requires a topological filter in the bulk. So for instance, if you want to understand the single chiral boson on the boundary, you must put U1 level K in the bulk, for instance. But if you want to put bosons moving on the E8 lattice, chiral bosons, you do not need to put anything in the bulk, just a contact term. So when we add stuff on the boundary, if we're going to abide by the rule that we're not allowed to change the anyons in the bulk, we might add, for instance, many copies of these chiral bosons that are moving on the E8 lattice, coupled in any way you want to each other and also to the bulk. But we are not allowed to add to the boundary a single chiral boson. That just doesn't make any sense. So the single chiral boson needs to end on non-trivial anyons in the bulk. More generally, how do you know if a system that you add on the 2-dimensional boundary requires some anyons in the bulk, or whether it can be put, or whether it can be studied on the boundary without any anyons in the bulk, but just an invertible filter? So the point is that the difference between C left and C right has to be a multiple of 8. That's a very important and necessary condition. And why? That's because then the Alvarez-Gomez with an anomaly, this is the Alvarez-Gomez with an anomaly, is properly quantized. If you put a single chiral boson, it will have a coefficient of 1/96, and then it's not properly quantized. It's not a good contact term. But if you had 8 chiral bosons moving on the E8 lattice, you get 1/12 to 1/12 pi times the gravitational Chern-Simons term in 3 dimensions. And this is properly quantized. You don't need to worry about it. So in principle, I'm just laying out the rules of what boundary conditions mean. You can impose any boundary conditions on the gauge fields. You can couple them to systems that maybe introduce some contact terms in the bulk, and that's it. So this more or less characterizes all the possible boundary conditions. Of course, there are infinitely many things you can do, but the rules of the game are somewhat restricted if you don't want to change the 2 + 1 dimensional bulk beyond changing the invertible part, or beyond changing the contact terms, which is equivalent. So this is C left minus C right. which I'll sometimes denote by C minus. Okay, so that's what I said here. So these are the rules of the game. That's how you can study the most general boundary conditions. And now we can try to discuss the question of when a gapped boundary condition exists a little bit more intelligently, a little bit more generally and concretely. Suppose you're given a theory of anyons. And I'll assume that this theory of anyons, doesn't contain trivial transparent anyons. So I'll just assume here, I didn't say it when I wrote it, but I'll just assume that only the unit enyon is transparent. Okay, so I'll just assume that there are no auxiliary transparent enyons because those are just contact terms. So when I say enyons, I mean that the braiding is non-trivial with some other enyon, that the braiding is non-degenerate, or that the S matrix of the enyons is unitary. It's pretty much the same. So given a theory of enyons, you cannot therefore expect to compute the chiral central charge of the boundary modes better than just mod 8. Because you can always change it mod 8 by adding chiral bosons moving on the E8 lattice. You can always change it by something that's a multiple of 8, because by adding this E8 lattice chiral bosons, you don't change the enyons in the bulk in any way. So given a theory of enyons, we can at most hope to be able to compute the chiral central charge mod 8. But this is indeed possible. There is a formula that allows you to compute the chiral central charge mod 8 given the data on the enyons. Once you've, all you need to know is the quantum dimensions of the enyons. Then you compute this prefactor. And that you also need to know the spins of the enyons, which are just various phases, roots of unity. And then you have to sum over the enyons. So given a theory of enyons, under the assumption that there are no trivial enyons other than the unit enyon, we can extract the chiral central charge of the boundary modulo 8. Okay, and that's the best you can hope for in light of the previous comments.
Zohar, what does that assume about the enyons? Is abelian braiding part of this?
No, this is completely general. This is true for any, so mathematically, this is true for any modular tensor category. Physically, it's true for any topological field theory.
What if the bulk theory has local operators?
No, okay, so I'm sorry, I should have said it extremely concretely. This talk is only about 2+1 dimensional systems, which are topological filters.
But there are topological field theories that have local operators.
Topological field theory by...
But you mean something more restricted.
You mean local operators which are also topological?
Mm-hmm.
Okay, yeah.
Like twists of supersymmetric theories.
Yes.
Generally, yeah.
Yes. Yeah, I'll make this, so I'll make my assumptions a little bit more concrete just to address these various issues. I'll assume that the number of vacua on S2 is 1. Okay?
Thanks.
Just for simplicity. I think that once you include these things, you get something like a multi-fusion category, and I believe many things can be extended to that setup. Just for concreteness in this talk, I'll assume that the number of vacua on S2 is just 1.
Thanks.
And that should address your concerns, I hope. Does it?
Yes.
Okay. All right. So in light of what we discussed, it's not surprising that the theory of enyons cannot predict the chiral central charge. It can only predict it mod 8, because the theory of enyons does not come equipped with a prescription of what the contact terms are. It only comes with a prescription of what the enyon braiding phases are and the S matrix and all these things. But so that's not surprising. Now, many theories of enyons, you just do this computation. You take the quantum dimensions, the spins, you do this computation, and you find that the chiral central charge is 0 mod 8. There are many such topological field theories. I'll give you many examples in this talk. If you just a very naive field theorist like me, you would say that these models are guaranteed to have a gapped boundary. And let me tell you what's the logic. So if the chiral central charge vanishes mod 8, I can always add on the boundary a bunch of chiral bosons moving on the E8 lattice, so copies of chiral bosons moving on the E8 lattice, such that the actual gravitational anomaly of the boundary vanishes, namely the Alvarez-Gomez Witten anomaly actually vanishes on the boundary. So by this, I mean that I can always arrange for the chiral central charge to be not just 0 mod 8, but I can actually arrange for it to vanish because I can add these chiral bosons moving on the E8 lattice. I remove the gravitational anomaly completely. By that, I mean that C minus is just 0 and not just 0 mod 8. And a naive filterist like me would say, okay, so there is no gravitational anomaly on the boundary. Why would there be gapless modes? You would now maybe be able to write down some couplings among these chiral bosons and whatever you had before, and just drive everything to a trivial phase. Okay, so the surprise in this field is that this is not true. There are many theories of anyons which have vanishing chiral central charge mod 8, but they do not admit a gapped boundary whatsoever. I see there are some questions. Let me stop here for question to see what's the question. Yes, I also, okay, there is a question of whether I'm assuming unitarity. I haven't assumed unitarity yet. Let me just put it this way. There will be some points maybe where I'll assume unitarity, but, well, did I assume unitarity? I believe I have not assumed unitarity yet. So let me just leave it at that. Okay, so the surprise in this field, as far as I'm concerned, is really that there are systems which have a vanishing gravitational anomaly on the boundary, but they are still gapless. And the question is, why does this happen? And how can we diagnose it, given that the ordinary chiral central charge is not enough? We can make the ordinary chiral central charge vanish, and it still doesn't admit the gapped boundary. So C minus, which is the chiral central charge, mod 8, is the only ordinary anomaly. So what's going on? And here...
Question.
Yes.
Assuming you take in the bulk two decoupled theories, which happen to have the same central charge, and just flip the sign of one of them.
Yes.
Then would that be an example?
No. So there is I assume, was this Nari?
Sorry?
This sounds like Nari's voice. I assume it's Nari.
Yeah, it is not his voice. Nobody else has this funny accent.
Okay. I think I have a similar accent for similar reasons. But anyway, let me just make a remark that I'll maybe mention again. If you take any topological field theory T and you tensor it with its time reversal, I think that's what Nari asked about.
No. I want the time reversal of T prime. With T and T prime just happen to have the same C.
Okay.
So I take two theories, T and T prime, which have the same C.
Yes.
And consider the theory in the bulk T times T prime bar.
Yes.
And T and T prime are two random theories.
Okay. And what is the question?
Sorry?
And you're asking whether there are examples in this class?
But there are tons of examples like this.
Okay. So what is the question?
But will these be examples of, you said that you're very surprised that there are
Yes. Yeah, there are simple examples in this class you mentioned. So I'll talk about it in more detail below. Consider U1 level 2 times U1 level minus 4. I believe this is the
example, yeah.
Yeah, this theory does not have a gapped boundary, even though C minus is 0. Okay.
Yeah, but there are tons of examples. Look at the construction I wrote, and then you can construct others by quotienting this by anything, etc.
Yeah. Nari, I'm just saying that there are tons of examples like that, yes.
Yeah. So why did you say it is surprising that there are such examples?
Well, the question is, what protects the boundary given that the ordinary chiral central charge vanishes? So in this talk, I'll introduce higher chiral central charges, and I'll argue that there is a gap, that only if they vanish, there could be a gapped boundary. So I'll introduce additional obstructions that go beyond the usual chiral central charge. Maybe I should not, I think Nati is saying that I should not have said the word amazingly. because there are some examples which are very simple, like U1 level 2 times U1 level minus 4, which does not have a gapped boundary. Okay. But the point of the talk will be to understand this phenomenon a little bit more systematically. So there is a mathematical, I believe the red color is very badly visible. I don't know why. On my slides, it's very clear. But there is a mathematical structure that many people in the audience know very well, which is called the Witt group. I will not explain very much the mathematical point of view. I'll try to focus more on the physics in this talk. But this is a subject that was developed a couple of years ago. And there are very nice papers just from this year, last year. And essentially the problem of the Witt group, I'll just say it physically, is to understand why some theories. So the problem of the Witt group physically is exactly in this kind of setup. So people would say the Witt group is saying that if T times T bar prime has a gapped boundary, then T is deemed equivalent to T prime. So they introduced an equivalence relation, which is that two theories T and T prime are deemed equivalent if T times T bar prime has a gapped boundary. It's just an equivalence relation. So clearly this is the correct kind of group structure to think about the question of gapped boundaries. And the reason that this is called the Witt group is because it's analogous mathematically to the classical Witt group that people have studied ages ago when they discussed the Witt group of ordinary fields using quadratic forms. Okay, so these are the examples that I already mentioned. So look at the few examples just to orient yourself. This theory has vanishing chiral central charge, but no gapped boundary. This one does admit a gapped boundary, and it has vanishing chiral central charge, of course. And also this one admits a gapped boundary. In fact, there is a simple result that if you take any theory and tensor it with itself time reversed, it always admits a gapped boundary. So in the Witt group sense, any theory is equivalent to itself. Sorry. Okay, one more comment about this equivalence relation is that if two theories, T1 and T2, admit an interface which is gapped, it's the same as saying that T1 bar times T2 admits a gapped boundary to an empty face. This is called the folding trick, that you start from two theories separated by an interface, you fold it like that, and you get just a tensor product of two theories to an empty theory. Okay, this is just the usual folding trick. So what I'm saying here is that the problem of understanding interfaces between topological field theories is very closely connected to the problem of understanding gapped boundaries. These are almost the same problem. If you specify that your interface has to be gapped, it's literally the same problem. Okay, are there any questions about that? And I'll start with some more detailed discussion of this problem. Are there any questions? Okay. Let me just start from a geometric picture. This geometric picture is very, very useful. So you can think about any three-dimensional space. It's very useful to just start from R3. You can think about R3 just for concreteness. And you can try to investigate the consequences of having a gapped boundary, right? So one thing you can do is to just have a plain boundary, like in the quantum Hall state. Another thing you can do in the quantum Hall sample, usually that's what they do. Another thing you can do, which is more maybe harder to engineer in the quantum Hall state, is to cut out a tube. So we cut out a solid torus. So we cut out from the space something that's just isomorphic to a disk times a circle. So the disk is the cross section of this tube, and the circle is is the angle along this tube. We cut it out, and we put topological or gapped boundary conditions on the surface. The surface is a torus, and we put. Now I use the word gapped boundary condition and topological boundary condition interchangeably. This is physically justified because if the boundary is gapped, it means that it doesn't have a displacement operator. And that means that you can change the location of the boundary without changing partition functions, at least in the low energy approximation. So the big point about this kind of boundary conditions is that, yes, they are gapped, but really what one is using is that they are topological. You can change the locations of the boundary without paying a price, as long as you don't intersect anything, of course. So since the boundary condition is gapped, that's what I said, and that means that it's topological, we can shrink the tube. And this is one thing that we cannot do for ordinary boundary conditions, for instance, those that were studied in the 80s by Elitzur, Seiberg, Schwimmer, and more. So in these boundary conditions that are gapped, we can shrink the torus, and it's really just a sum over anyons. So by shrinking it, we get a sum over anyons. Because when we shrink it, it becomes infinitesimal. We can think about it as a world line of anyons. So the big deal in this business is that the boundary condition is equivalent to a linear combination of anyons with some coefficients, which I will call Z0A. And these coefficients are some non-negative integers. Okay, so the partition function on any three manifold with this kind of tube removed and gapped boundary conditions is the same as the sum over Z0A times the partition functions of just unknots of the enyon A. Now you can also geometrically prove that Z00 is 1, meaning the trivial enyon must be present in this linear sum that is equivalent to a topological boundary condition. How do you prove that? Well, you just, instead of taking out from the manifold something that's isomorphic to a solid torus, you can take out something that's really isomorphic to a three-sphere, but you elongate it. And now it ends on the unit enyon because it ends nowhere. I mean, there's nothing that on the other side. So that means that the homomorphisms from the unit enyon to this sum are non-empty, and you can then do a few more steps and prove that it actually has to be 1, that the unit enyon has to appear exactly once inside this linear combination. So the unit enyon is always part of this linear combination that represents a gapped boundary. So on the one hand, the partition function on this three manifold can be written like that. It's just a sum over enyon world lines with some integer coefficients. But on the other hand, it's also the partition function on this topological, on this space, which is that's original space removed, from which you remove the solid torus with trivial boundary conditions. And this leads to an equation relating the original partition function, a linear sum over the quantum dimensions of the corresponding enyons. And the quantum dimensions appear just because the expectation value of this is the quantum dimension. And then the partition function on the space with the solid torus removed. And this equation is interesting for the case of the three-dimensional sphere. It's interesting for many spaces, and it's one of the things that I'll explain. But for the case of the three-dimensional sphere, this equation immediately gives a very interesting result that makes our physical intuition precise. So if we take the three-dimensional sphere, one thing is that if you take the three-dimensional sphere and remove a solid torus, you get another solid torus with gapped boundary conditions. That's on the one hand. On the other hand, here we have ZS3. This is becoming ZS3, and this is some sum over quantum dimensions. But the partition function on a solid torus with gapped boundary conditions is just 1. So this partition function is just 1 because we have a gapped boundary, so there are no chiral modes, and the partition function of the disk is therefore just 1 because there are no states on the boundary. So this leads to a very nice equation that tells you that the S3 partition function is given by 1 over a sum which includes some integers and some quantum dimensions. And this is very much related to some very recent nice work by Fried and Telemann. Just a very simple derivation of some fact that the three-sphere partition function in a theory which has a gapped boundary is constrained in this fashion. But on the other hand, there is the usual formula for the three-sphere partition function. Sorry, this is not Z3, this is ZS3. there is the usual formula for the three-sphere partition function that I've already mentioned before, through which you can define the chiral central charge. So the three-sphere partition function, famously after the work of Witt on the Jones polynomials, we know that the three-sphere partition function is sensitive to the chiral central charge, mod 8. And comparing these two expressions, we arrive at what I said, that for a theory that has a gapped boundary, it must be that the chiral central charge vanishes. It's just because we see here that the partition function is a positive integer, a positive number. And here there is an arbitrary phase. So therefore this phase must vanish. It must be 1. This phase must be 1. So this gives you a very nice geometric proof of the deep fact that the chiral central charge must vanish mod 8 in theories with a gapped boundary. Now you could ask yourself whether this nice derivation is limited to the three-sphere. Can we do something like that for many other spaces and derive additional constraints on the existence of a gapped boundary? And the answer is yes. I'll now go through the abelian theories and then non-abelian theories, and I'll give you many invariants that must be positive or 0 in some convention for a gapped boundary to exist.
Question. So
yes.
You said that you have gapped boundary, so the partition function is 1. So why can't there be ground state degeneracy or something like that?
Right. So oh, you're asking about this setup, right? Right. So the states on the boundary are classified by some representations of Virasoro. Well, let me just put it this way. I'm assuming now that the theory on S2 has one trivial vacuum. So when you have a disk with a gapped boundary, that has to have a single, just one state. It's closely related, I believe, to Tudor's question. So I can add here something that would make you totally happy. So I can just add gapped and trivial. If you want, I can just limit every time I said gapped, I can just say gapped and trivial, and then everything will be. I'll just keep saying gap, not to make it inconvenient for me to say, but when I say gap, I mean a gap trivial boundary with one ground state. So maybe I'm answering the question tautologically, but that's what I mean when I say gapped.
It looks like the result would hold even if you replaced 1 by some other integer.
That's right. So even if this was some other integral number, and it would still hold. But in this, I'll derive some constraints on normalization of some partition functions if I have enough time. So I would like just to make this assumption that this is 1 for now. It won't be important whatsoever for many things, but for some small things at the end, it might be important. Okay. But yeah, indeed, it doesn't actually matter at this stage. So let me just try to convince you that there are many other invariants that go beyond the chiral central charge for this problem. So let's think about abelian theories first. For abelian theories, I'll now give you many obstructions that go beyond the chiral central charge for the existence of a gapped boundary. And these obstructions are geometric in the sense that they are calculated by partition functions on some spaces. And you can make a similar argument by plucking out some tori, putting back something else. You can make geometric arguments using the existence of a gap boundary that those partition functions have to be positive. So that's the idea. So now I'll tell you which spaces you are allowed to use. So for abelian, the reason that I'm specifying it to abelian now is that the partition functions of abelian topological field theories on various spaces, they are sensitive only to the essentially homology of that space. So the homology of the space is some group, And it's sensitive essentially only to the homology. For non-abelian theories, also pi1 is important, for instance. But for abelian theories, only h1 is important. Or in other words, if you construct the space on which you are going to compute the partition function by removing some link and putting some new link with some twists, perhaps, all you need to know for abelian theories is the linking matrix. It's just the matrix that you need to know. While for non-abelian theories, also the isotopy of the knot is important. So I'm going to discuss manifolds M3, which are obtained from the three-sphere by just surgery. We remove some link, we put something back, and we have a linking matrix. So it's all specified by one symmetric matrix. Okay. So this defines a space with a certain homology, and the dimension of the homology group is the same as the determinant of this matrix. This is the dimension of H1. The matrix L specifies the full homology group, not just the dimension of H1. It's just a quotient of the integers, some lattice of integers, modulo integers that can be obtained by acting with the matrix L on other integers. And now I'll give you the main claim about these theories. The first main claim: if the greatest common divisor of the homology space of the rank of the homology of the manifold and the number of abelian anyons. So here I've introduced some notation that didn't appear before, and I'm only defining it later, but let me just say that for abelian theories, I'll use the notation G just to stand for the number of anyons, including the one transparent anyon. So if the GCD of these two integers is 1, then we have a theorem, which is that the partition function has to be a positive number. Or I wrote it more formally, the argument, namely the phase of the partition function, has to be 0 mod 2 pi. That just means that it's a positive number. Furthermore, it's a non-vanishing. So this phase is well defined. We can also prove that this partition function is non-vanishing. Let me just note in passing that if you don't satisfy this condition, this is just not true. First of all, there are many examples of theories with a gap boundary which are not positive numbers. And secondly, the partition function may even vanish, which cannot happen under these conditions. Okay. So this is a general obstruction. And I'll give you an example now. I'll skip this little comment and give you I have some example here. Well, are there any questions about the statement before I go into some examples? Okay, so let me go to some simple examples.
And how do you interpret the statement when the homology is infinite dimensional? Is there anything interesting there, or do you replace this with the torsion?
So for instance, on the torus, you just count the anyons and it will be trivially satisfied. The torus partition function just counts the number of anyons. I can't give you a completely general answer. I do not know the general answer. Yeah, this statement only holds if you can obtain the said manifold by some finite linking matrix.
You can obtain any 3 manifold by surgery on a link. It seems like some extra, but it's totally fine to just assume that you do it in such a way that the homology is finite.
Right. This is just a statement about a class of partition functions. So we claim that all these partition functions are like order parameters for this problem of gap boundaries. Let me just give you a quick example. The simplest linking matrix is just an integer. So the linking matrix is a 1 by 1 matrix that's just equal to some number n. Sorry, it's already written here. This defines a surgery for the so-called length spaces, of which the first example is just a 3-sphere. So if L is 1, we haven't done anything. It's just the original. And this corresponds to just a surgery on such a funny a knot which is twisted n times. And if you just twist it one time, it's the same as the tree sphere in some framing. And this is the partition function for the length spaces. This is true for both abelian and non-abelian theories. For abelian theories, you can remove these quantum dimensions because they're all one in abelian theories. And also this is just the dimension of the group of anyons. So for abelian theories, it's just 1 over the number of anyons times the sum over the topological spins to the power n. And the claim is that you can define higher central charges. So the length spaces give you examples of the higher central charges. These are special cases of these linking matrices, which could be co-prime with the number of anyons. So if n is co-prime with the number of anyons, this phase is like a chiral central charge. It's a generalization of a chiral central charge. So this is the theorem, that a gapped boundary means that all these phases must vanish mod 2 pi. Or in other words, the said partition functions must be positive. And this is, I think the notion of higher central charges is good because the case of 1, n equals 1, is just the ordinary chiral central charge mod 8. So a particular example of this is the vanishing of the chiral central charge that I mentioned, mod 8, that I mentioned before. I think there is some issue with the convention. Yeah, I think I forgot 2 pi. Here I have to put 2 pi. And then it's literally true. Okay, so Cn is what we will refer to as higher central charges. And they are defined as long as this condition is satisfied. And there is very nice mathematical work on these sums, that appear for such values of n very recently by these papers. Just from some of them are very recent. These papers are very recent. So let me just give you, just to see that this is really working. Let me give you the first non-trivial example that I already mentioned to Nari. It's just this theory. We can of course verify that there is no gapped boundary using standard techniques of studying the boundary conditions. It's just an abelian theory. It's very simple. But let me just show you that the formalism works. This is the complete list of spins in this theory. You don't have to, I can walk you through the details, but it's boring. It's just the list of topological spins of the 8 anyons. There are 8 anyons here. And this is the tree sphere partition function. I just computed it explicitly here, and nicely it's a positive number. And indeed, the chiral central charge vanishes. But if you take the first case of an integer whose GCD is 1, this is the third length space, so we're talking about Xi3, you compute and you find a negative number. So that means that Xi3 is pi, which is non-zero mod 2 pi. And therefore, this model cannot have a gapped boundary, and that's it. And we have arrived at this conclusion by just summing over the topological spins without ever having to write the boundary conditions, quantizing the model, or studying the two-dimensional RCFT that is obtained with some boundary conditions. So you can immediately conclude that this model cannot have a gapped boundary due to the non-vanishing of the third higher central charge. Are there any questions about this example? Good. You can ask now more sophisticated questions. Are there abelian theories for which all these higher central charges are actually vanishing mod 2 pi? So there is no obstruction as far as the Cn go, but actually still a gapped boundary doesn't exist. Okay, this is now a more difficult question. And the answer is yes. This is the simplest example. You can also prove that in some sense it's the simplest example. This is the simplest abelian topological field theory, for which if you sat down and computed all the Cn, you would find that they're all 0 mod 2 pi, all the allowed Cns. You have to pick n correctly so that the GCD vanishes. So all the Cns vanish, but it still does not admit a gapped boundary. How do we know that it doesn't admit a gapped boundary? Well, let's say you can compute it you can just check that it doesn't. And you can ask, maybe there is an extension of the chiral central charges that would be more exhaustive. That would be an if and only if. And here I'll just quote the result. I'm not going to prove it, but I'll just quote it. It's one of the main results of our upcoming work. You can enlarge the space of the GCD condition. So previously, remember that we required that the allowed ends satisfy this. But you can allow for more ends, such that GCD of n with some funny combination here is 1. NFS, well, I have to define NFS. NFS is the Frobenius-Schur indicator. The simplest definition of it is that it's the smallest integer, such that all the topological spins are roots of unity when raised. Sorry, all the topological spins are NFS order roots of unity. And you know that such an integer exists because there is a theorem that such an integer exists by Vafa. But more concretely, for abelian theories, it's also very easy to prove that NFS divides 2G. It doesn't divide G, but it divides 2G. So NFS is a very explicit integer that has the same prime factors as G, but it can be twice. It can be 2G in some cases. Anyway, so this enlarges the set of integers for which we can define higher central charges. And now we have an if and only if theorem. If all those chiral central charges, if all those higher central charges vanish, then there is a gapped boundary. So it's an if and only if theorem now. And this gives a complete classification as far as central charges go. So if you just measure those central charges, by measure I mean compute, you have a complete classification. Let me mention some very simple result that follows from this work. You can prove that any abelian theory, you can prove that if an abelian theory has a gapped boundary condition, it's actually a digraph-Witten theory. A digraph-Witten theory is a discrete gauge theory based on a abelian group, a finite abelian group. So using this thing, we prove that we prove this little fact that any abelian. First of all, one direction is trivial. Any abelian digraph-Witten theory has a gapped boundary. You just condense all the gauge fields. The other direction is much less obvious, that every abelian theory that has a gapped boundary is secretly a digraph-Witten theory. But this follows from some things that I am not going to explain. I don't have enough time. Okay. Now I'll say some things about the non-abelian case. And then I want to say something about RCFTs and also about the 3D correspondence. And I only have 9 minutes, so I'm going to rush now. Hopefully you got the main point, so I'm going to rush a little bit. You can ask, does any of that carry to non-abelian theories? And the answer is yes. There is a similar GCD condition where NFS is defined as before as the smallest integer, such that all the topological spins raised to that power are 1. And these are obstructions even for non-abelian theories. So these higher central charges can be defined also for non-abelian theories. There are more facts that you can prove about these higher central charges, but I'm going to jump to the RCFT. I think this is a very interesting and very cute way to think about gapped boundaries. And I want to explain the RCFT point of view. And I'll be a little bit more pedagogical now and then jump further. So let's suppose that we start from a Chern-Simons theory with the standard Dirichlet boundary conditions. The standard Dirichlet boundary conditions is essentially, Moore-Seiberg, but I think more concretely, Elitzur, Moore-Seiberg, and Schwimmer. So let's just start from the current algebra boundary conditions for a Chern-Simons theory. One of the main facts that they've shown is that if you pierce your disk on which there are current algebra, this is the current algebra boundary conditions. If you pierce that disk with an anion A, the partition function is the character, chiral character of the corresponding representation of the current algebra. Now I want to tell you something about the annulus. So just to explain the 2D story, it's very interesting to consider an annulus geometry. When on the outer disk, you put the Elitzur, Moore, Seiberg, Schwimmer boundary conditions, which lead to chiral edge modes transforming under some current algebra. But on the inner circle, you put our gapped boundary conditions, assuming that they exist. This leads to a very interesting construction that it allows to interpret the RCFT point of view on topological boundary conditions. So the main thing here is that, as before, because the inner boundary is gapped, it's topological, so you can shrink it. And you get the sum over enyons with these funny coefficients that we've seen at the beginning of the talk, the very same coefficients. And now using this work of Elitzur et al., this is this disk partition function is just a sum over chiral characters. But now, because this is an annulus partition function, it has to be modular invariant. So what's the big takeaway message? The takeaway message is that in terms of the RCFT, the condition that there is some boundary condition that is gapped is just a statement that the chiral algebra can be extended to have one character. And that leads to a modular invariant partition function, which is completely holomorphic. I forgot to write the word holomorphic. So using this technology, you can just look at RCFT examples and try to understand when such a matrix exists. This is a highly non-obvious problem, but it's a way to think about it. You can also write this condition in terms of the S matrix. It's an if and only if condition in terms of the S matrix. If there are eigenvectors of the S matrix with eigenvalue 1, which are integral matrices ZOB, integral vectors ZOB with eigenvalue 1, that's enough to write down a holomorphic partition function, and that's necessary to have for having a gapped boundary condition. Okay, so here I just derived quickly some sufficient conditions that necessary conditions that follow from that, but I won't go into it as I'm running out of time. I just want to make a quick comment that relates this story to Kapustin's Saulina. So this point of view using the S matrix makes it clear that this subject is very much connected for abelian theories to having a Lagrangian subgroup of enyons, or in terms of one-form symmetry, it's equivalent to having a non-anomalous one-form symmetry of sufficiently large dimension. I'll just make it quickly it's a quick comment for the experts. I won't go into that. Clearly, one thing here that is missing is a very clear physical interpretation of these higher central charges. Why are these partition functions, we call them higher central charges, or people have called them higher central charges because they're they're like interesting order parameters for the problem of gapped boundary. But is there a more physical way to think about it? So one hint comes from recent work of Harvey, Hu, and Wu, in which they've suggested that in the language of RCFT, these higher central charges could, I mean, they've done some work that's independent of this, but if you take what they've done and you take some things that we have done and combine them, you can arrive at some interesting suggestion that these higher central charges can be viewed as the physical chiral central charges of some new RCFTs that are obtained from the original RCFTs by the action of something that's called the Hecker operator. And for reference, you can just look at this paper. I won't go into that. I'll finish with one last comment about a possible relation to the 3D correspondence. So for abelian theories, you can specify them with the K matrix, and you don't lose any generality by doing that. This was shown many years ago, and you can look at Belov and Moore for references and proofs. There is a magic identity that we've exploited throughout our work, which I mean, again, I haven't described, but this identity seems like it's suggesting at some interpretation coming from the 3D correspondence. So the identity is that if you take a Chern-Simons theory with K matrix K, compute the partition function on a 3-manifold obtained by surgery on a link L, up to some phase, which is an 8th root of unity, and some prefactor that maybe has a geometric interpretation in the 3D correspondence, you get a partition function where L and K are exchanged. And this is only true when the GCD condition, exactly the same GCD condition that we employed in our work, is utilized. So we've used this magic identity that we've proven for many little applications. But the fact itself that there is a symmetry between the surgery linking matrix and the K matrix is very suggestive of some geometric interpretation. So that's all I wanted to say. Thank you. Shuheng told me yesterday that maybe people will want to see proofs of these facts that these are good order parameters. So I've added like a lot of material here trying to summarize the proof, but I obviously don't have time for it, but I'm happy to explain it if somebody wants to stay over time.
Thanks very much, Zohar. Right. Yeah, we'll take questions, and I guess there are quite a few, so we'll do them in the order of raised hands. I think Maisam is first.
Hey, Zohar.
Hi.
Thanks for the nice talk. I had a couple questions. One question is the usual central charge formula that you gave, for which you wrote as Z of S3. You can also think about it as a partition function of a four-dimensional theory on CP2, where the four-dimensional theory is determined by, the modular tensor category by this Crane-Yitter kind of formulation. So I'm wondering if what manifold would correspond to the higher central charges. So that's one question. And then the other question is, there's actually a classification of gap boundaries by Lagrangian subalgebras.
Yes.
Like distinct gap boundaries correspond to distinct Lagrangian subalgebras. So yes. Do you think these kinds of methods might be able to count the number of distinct gap boundaries, not just tell us whether there exists one?
Right. Okay. So let me start from the second question, because I can say much more about it. So there is another point of view on gapped boundaries that I have not emphasized, but it's more central, for instance, in the formulation of Fried, Telemann, and other authors, in which you have some kind of algebra enyon A. Algebra enyon A, which is a sum over semi-simple enyons little a, with some integers, okay? Positive integers, non-negative integers. And this particular algebra enyon A has to have various magic properties in order for this to define a gapped boundary. First, it has to have zero spin. It has to have vanishing R matrix, trivial R matrix, trivial F symbol, zero spin, and so on and so forth. But most importantly, its quantum dimension has to be the same as the square root of the total dimension. And there are lots of other properties. But typically finding such an enyon is extremely difficult. Let me give you an example. Take G2, take the Fibonacci enyon. The Fibonacci enyons have a non-zero chiral central charge, but if you raise them to the power 20, they have a zero chiral central charge mod 8. And it's extremely difficult practically to ask if such an algebra enyon exists. On the other hand, geometric invariants are easier to compute, because we can compute a partition function just by taking the elementary partition function of the Fibonacci enyon and raising it to the power 20. Similarly, if you want to understand like this model, it's abelian, but still it's far easier to compute partition functions because it's a direct product of many elementary blocks that we know. So yeah, these formulations are equivalent. And in fact, in many, I didn't explain all the results that we obtained, but in many things that we did, we used the formulation based on an algebra enyon to obtain some results about these higher central charges and vice versa. So we've used both points of view. Now, for the question about the four manifolds, I believe that maybe one of my collaborators would know the answer. I do not know the answer.
Well, just about that second question, but I was asking about counting the number of distinct gap boundaries.
Oh, okay. I didn't understand that. Okay. This counting the number of distinct gap boundaries is not something that we have thought about at all. For instance, if you look at Z2 gauge theory, of course there are two. At least, there is the condensation of E and the condensation of M, so there are at least two. Perhaps the other examples also have more than one option, but we have not tried to classify them or count them. I don't know if this would be something that we can do with our formalism.
Thanks.
Konstantin?
Yes, thanks. Let me just lower my hand before I forget. This is Konstantin Telemann from California, I guess, sunny California. Hey, thanks for the talks. I enjoyed it very much. But so I had a comment and question. So the comment is, I was going to refer you to a paper that Dan and I put up about a year ago, which loosely says that a three-dimensional TQFT has topological boundary condition if and only if it obviously does so. So let me try to make it a bit more precise, that the theories we've discussed that come from modular tensor categories, they will have topological boundary conditions if and only if their Witt group class is 0, and there's another cube root of unity that you have to worry about. That's a fine point. But there was one proviso in our theorem, that the theories had to be, and the boundary condition had to be fully local, which is made precise by saying that some functor extends down to a Bordes category with corners. So we had to use full locality of that. If we abandon that, if we don't have full corners, like three-dimensional corners, then I'm pretty agnostic about how much can be said. Now, from you didn't sketch out a complete argument, but it didn't seem to me you're assuming full locality down to corners. Is this something you want, or?
Yeah, so the main thing that we assume, and perhaps it's equivalent to your assumption, I'm not sure. So I'm just basically bouncing the question to you. So what we assume is that if we cut out a solid torus, okay, a solid torus, since it's a gap boundary, you can shrink it, and this can be replaced by a sum over just unknots of the elementary semi-simple anyons with some integer prefactors. This is what we assume. This is the main tool that we use to prove many, many results. We just use the fact that we can pluck out this solid tori, do some geometric manipulations, shrink them, twist them, and then we arrived at these obstructions for gap boundaries.
That's in the 3D. That's in the 3D theory, right? The full 3D theory.
Yes, this is D2 times S1. This is we pluck out the D2 times S1.
And it's maybe a weaker assumption than going down all the way to corners, unless you're cutting it down to cubes. You probably wouldn't, means you're not using the full locality for this. It seems to me, without just off the top of my head.
That's the main thing that we've assumed to prove many of the statements that I mentioned. How general it is, I believe it is. I think it assumes Poincare invariance. This is pretty clear because the S1, we assume some kind of nice symmetry on the S1. Yeah, I can't say exactly mathematically what this assumption means, but that's in practice what we use to prove these results.
Okay, thanks.
This is enough also to prove that in the RCFT language, you have a holomorphic partition function like this with the current algebra boundary conditions.
Yeah, no, that I think works only if you have the standard 3-to-1 dimensional part. You don't need points for that. I think that's. But actually, it reminds me of another comment. Sorry, I'm abusing my time here. In terms of, you mentioned the Kapustin-Saulina work, because it's something we thought about a long time ago, and I have a vague memory that, depending what you mean by gapped boundary condition, there may be a way to put gapped boundary conditions, meaning things that don't depend on conformal structures, even when we don't expect it. The price to pay is that it will involve infinite dimensional spaces. They won't be quite topological in the sense of staying in finite dimensional spaces, but they will be topological in the sense that they're not conformal anymore. They don't use a conformal structure. So depending exactly, again, what you want to assume about the boundary condition. I mean, that sometimes they can actually appear when you don't expect them.
Right. We would like them to end up being completely topological, not just independent of the conformal structure, but completely topological.
Thanks, Konstantin. And Zohar, any other questions? I had one that you guys may have partly answered. Zohar, you talked about computing like various three-manifold partition functions and defining central charges that way and using that to probe the existence of a gap boundary condition. I was wondering if there was some sort of more universal like topological classification of like what all possible higher central charges are, why they're associated to lens spaces, and maybe this has to do with the Witt group or.
Yeah, so I haven't had time to explain it, but it's actually an open problem in the following sense. So you remember that for the abelian theories, to arrive at a complete classification or an if and only if condition for the existence of a gap boundary, we had to improve the GCD condition.
Yeah.
A little bit. For the non-abelian case, and that's why I separated the talk into abelian versus non-abelian. For the non-abelian case, it's not possible. So we have not been able to improve this GCD condition to the one that appeared in the abelian theories. In the abelian theories, it was a more loose GCD condition that allowed more values of n, and then it led to a one-to-one. It led to a necessary and sufficient condition. Here, we have not succeeded in enlarging the space of allowed n's to arrive at necessary and sufficient conditions. So these are only necessary conditions. We don't have a complete list of invariants for the non-abelian case.
Okay, thanks. And maybe a trivial comment. In the construction involving a chiral boundary condition and a gap boundary condition, I guess what you said seems to extend to not just to torus partition functions, but to like arbitrary genus surface partition functions, and is maybe just even a local feature. It sounds like if you have both types of boundary conditions, you can collide them. Yes. And define you get a well-defined two-dimensional theory that has partition functions on any genus.
I believe yes. I believe there are. Yeah, you're asking what would you learn about, let's say, the genus 2 partition function from the gapped boundary. And sorry, where was that? Yeah, you can definitely try to extend this logic to that case.
Yeah, I guess my intuition is that collision should be local, and like what you really get is an ability to sort of turn that chiral boundary condition into a purely two-dimensional field theory.
A holomorphic one, I think. Yeah.
And which happens to be holomorphic.
Yeah. That's possible, yes. We didn't study it though.
Thanks very much for the talk. Are there any other questions, or if anyone wants to hear about the proofs at the end of the talk, I'm happy to make Zohar host. Okay.
They're not illuminating, but I mean, one of them is a little bit illuminating, I should say.
Great. Let me stop the recording then. Yeah, and let's all thank Zohar again. And if you send slides to me or to Dave Morrison, we'll put them up on the seminar website.
Yeah, thank you so much.
Thanks. Then everyone have a great week.
Bye-bye.